An Introduction to the Theory of Automorphic Functions by Lester Ford. Chapter 1. Linear Transformations. Section 1. The Linear Transformation. If Z is a complex quantity whose real part is x and whose imaginary part is IY, it is customary to represent Z by a point in the plane whose abscissa is x and whose ordinate is y, these coordinates being referred to perpendicular axis. If x or y or both become infinite, the point recedes to an infinite distance from the origin of coordinates. This is expressed by z equal to infinity, and infinity is considered to be a single point in the complex plane. In this respect, the conception of infinity differs from that employed in projective geometry, where the infinite region is considered to be a line. Consider z prime equal to f of z, where f of z is a function of z, and let the variable z prime be represented on a second plane. To each point z for which the function f of z is defined, there corresponds one or more values of z prime given by the above equation. To points, curves, and areas in the z-plane, there correspond, by virtue of the equation, points, curves, and areas in the z-prime plane. The configurations in one plane are said to be transformed into configurations in the other plane. The whole theory of automorphic functions depends upon a particular type of transformation defined as follows. Definition: the transformation z prime equal to az plus b divided by cz plus d, equation 1, where a, b, c, and d are constants, real or complex, and ad minus bc is not equal to 0, is called a linear transformation. A reason for this is that the kind of transformation most frequently considered in the theory of functions of a complex variable form the infinite region into a point in the infinite part of the plane, whereas ordinary projection in geometry transforms the infinite region into a line. Also called a linear substitution, a homographic transformation, or a homographic substitution. If AD minus BC is equal to 0, the equation reduces to z prime equal constant, but this case is without interest. The quantity AD minus BC is called the determinant of the transformation. It will be convenient to have always AD minus BC equal to 1, equation 2. The determinant in the general case taking this value if the numerator and denominator of the fraction in the second member is divided by plus or minus the square root of AD minus BC. Let equation 1 be solved for z. Then z is equal to minus dz prime plus b divided by cz prime minus a, equation 3. This is called the inverse of the transformation of equation 1. It is a linear transformation with the same determinant as 1. We state then, Theorem 1, the inverse of a linear transformation is a linear transformation. To each value of z, there corresponds one and only one value of z prime by equation 1. And conversely, to each value of z prime, there corresponds one and only one value of z by equation 3. In other words, the z-plane is transformed into the z-prime plane in a one-to-one manner. It will be most serviceable to represent the value of z prime not on a different plane, but on the same plane and with the same system of coordinates as are used for representing z. In all that follows, but one plane will be used unless the contrary is explicitly stated. The results just found can be stated in the following. Theorem 2, the z-plane is transformed into itself in a one-to-one manner by a linear transformation. Let the points z prime be subjected to a linear transformation. Z double prime is equal to alpha z prime plus beta divided by gamma z prime plus delta, equation 4. Expressing z double prime as a function of z, z double prime is equal to alpha times the quantity az plus b divided by cz plus d plus beta, all divided by gamma times the quantity az plus b divided by cz plus d plus delta, equal to the quantity alpha a plus beta c times z plus alpha b plus beta d, all divided by the quantity gamma a plus delta c times z plus gamma b plus delta d, equation 5. Making the transformation 1 and then making 4 is equivalent to the single transformation 5. Now 5 is also a linear transformation. Its determinant, in the form in which the fraction is written, is the quantity AD minus BC times the quantity alpha delta minus beta gamma. It is worth noting that if the determinants of 1 and 4 are each unity, the determinant of 5 is unity also without further change. If z double prime be subjected to a linear transformation, we get again a linear transformation of z, and so on. And thus we have, in general, Theorem 3. The successive performance of any number of linear transformations is equivalent to a single linear transformation. The linear or homographic transformation has the property that it leaves invariant the cross ratio of 4 points. For if z1, z2, z3, z4 are 4 points and z1 prime, z2 prime, z3 prime, z4 prime are the points into which they are transformed, we have, on substituting for z1 prime, z2 prime, z3 prime, z4 prime, their values from equation 1, the quantity z1 prime minus z2 prime times the quantity z3 prime minus z4 prime divided by the quantity z1 prime minus z3 prime times the quantity z2 prime minus z4 prime, equal to the quantity z1 minus z2 times the quantity z3 minus z4, all divided by the quantity z1 minus z3 times the quantity z2 minus z4, equation 6. An Introduction to the Theory of Automorphic Functions. This book was written by Lester R. Ford, M.A., Harvard, lecturer in mathematics in the University of Edinburgh. It was published in 1915 by G. Bell & Sons Limited, London, and is now in the public domain. It is read by Jim Renholt with programming and illustrations by Jim Renholt in 2019. Thank you for listening.